Hello, everyone, and welcome to Console Room 2025. I am Michael Zecca, and I will be giving you a little presentation today about the approaching solar maximum and the relationship between that and the frequent auroras, or northern lights, and southern lights that we've been seeing a lot of in the last year and that we'll be seeing a lot more of in 2025. Just to give you a little bit of background on me, I did start off originally planning to study astrophysics for a career. I did do an undergraduate training in that area, majored in physics and mathematics, took a lot of astronomy courses, worked in a few different fields related to planetary science, stars, and so on. Solar physics isn't my specialty per se, but I have learned a little bit about this over the years. And while I no longer do work in astrophysics, I did spend about a decade of my life as a high school physics teacher, and these days I'm actually an associate librarian with Hennepin County. Anyway, to go forward with this, I also did not grow up in the north, in Minnesota, like many of you here. For those of you my age who grew up in Minnesota, you probably did experience a number of auroras in your earlier years. The sun was far more active in the 80s than it has been the last couple of decades. I've lived in Minnesota about 20 years, and the sun has been pretty quiet for a lot of that stretch. So this past year has been quite exciting for me and frankly for a lot of the globe. Let's get started. First of all, what is the sun? And here's a scene from Airplane 2, the sequel. Simon says, "My God, the sun." "What is it, Simon?" "The large fiery ball at the center of our solar system, but that's not important right now." Well, large fiery ball at the center of our solar system isn't far off the mark, but it is actually quite important when it comes to producing auroras. So, a little bit more about the sun. The sun is a main sequence G2V yellow dwarf star. So what does that mean? It's a pretty run-of-the-mill middle-aged star. It's on the smaller side. When I say dwarf star, the sun is not real big when compared to giant stars like Betelgeuse or Rigel. But it is, pretty run-of-the-mill, average little star. Primarily yellow in color, at least that's what we say. I'll get more into that in a little bit. It is basically a huge ball of hot plasma, and if you're not sure, you don't remember from high school chemistry what a plasma is, that's an ionized gas. The electrons have been stripped off the atoms and are flying around freely because it's so hot inside. There's just too much energy to keep those bonds. So you basically have a lot of atomic nuclei and electrons swimming around together. And since the sun is primarily composed of hydrogen and helium, a lot of that is just individual protons flying around, which we also talk about as a hydrogen nucleus. All right, and the sun is about the same diameter as 109 Earths. You could put 109 Earths across the equator and get the same width. Or you could fill the sun with about 1.3 million Earths. The mass of the sun is about 333,000 times the mass of the Earth. Now you might be noticing that volume is much higher compared to the Earth than the mass. And that's again because the sun is primarily composed of hydrogen and helium, which are the lightest elements. The Earth, of course, is made up a lot of heavier elements as well, like silicon, oxygen, nitrogen, and so forth. All right. Well, moving along, how hot is the sun? So the Stefan-Boltzmann law and the Wien displacement law describe a relationship between the color frequency that is the brightest coming from a star and its surface temperature. So, you've got kind of a bell curve of different colors coming off of a star, but the one that's coming out the most is related to the peak temperature of the star. This has to do with black body radiation. If you think of a human being as a black body radiator, you have a peak color that you're emitting as well. In the case of the sun has a surface temperature of about 5,800 Kelvin, give or take a couple hundred, or measurements of this vary depending on the experiment. That would equate to about 5,500 Celsius or about 10,000 degrees Fahrenheit. That corresponds to a peak color frequency that's around 500 nanometers. That's kind of a yellow-green color, so it's really not true to call the sun a yellow star. It's more of a green star, but it is so intensely bright we don't see it as green. We see it as more of a yellow-white. That being said, if you think about the spectrum of colors that the human eye can see, with red at one end and blue at the other, green falls somewhere in the middle, and there's a reason for that, and that is the sun. Our eyes are tuned to that brightest color from the sun. The center of our color spectrum that we can see with our eyes is basically the same as that brightest color coming from the sun. If we lived around a red supergiant like Betelgeuse or a red dwarf star like Proxima Centauri, our visual spectrum might be centered in the red. Those are cooler stars with a surface temperature around 3,000 degrees Celsius. If we lived around a hot blue-white star like Rigel, that peak temperature might be more like 10,000 degrees, which gives you a bluer color, and so your visual spectrum would probably focus more on the blue. You wouldn't see in the red very well, but you'd see into the ultraviolet very well. And if you think about human beings, we radiate our highest frequency in the infrared. When you think of heat, when you're thinking about a flame or a hot oven, you're usually thinking about infrared light. Now, if you get down deep into the core of the sun, it is much denser and much hotter. We believe the temperature of the sun down there is about 15 million Celsius, or about 27 million Fahrenheit. That's quite a bit hotter. Those are the temperatures at which you get nuclear fusion going on. There's really not as much fusion going on up at the surface of the sun, but it does take a good long time for the energy produced by nuclear fusion to work its way from that hot core out to the outer surface so it can radiate out into space. I was watching a video just earlier this morning with Neil deGrasse Tyson where he described that it's taking 10 to 100 million years for the energy produced by fusion down inside the core of the sun to work its way out to the surface. Okay, so again, nuclear fusion. Another way that you could describe a star like the sun is it is a giant naturally occurring nuclear fusion reactor. So there is, again, primarily hydrogen and helium inside the sun, and when you get it at those ridiculously high temperatures, you can get those nuclei together, and you can start breaking bonds at the nuclear level and creating new ones. So these equations that you're seeing on the screen are not chemical reactions, these are nuclear reactions. So deuterium is a heavier form of hydrogen that has absorbed one neutron. So it has an atomic mass of 2. If you get two deuteriums together, with fusion, you can actually break some bonds and fuse things back together and produce a helium-3 nucleus and an extra neutron and some extra energy in the amount of 3.27 mega electron volts, to use a weird energy unit that physicists like to use when describing nuclear reactions. You can also, depending on which bonds you break and which ones you reform, instead make, out of two deuterium atoms, a tritium atom, which is a hydrogen with 2 neutrons, and a standard hydrogen atom, and that produces about 4 mega electron volts. And that excess energy is coming from mass that is lost along the way, that is dictated by Einstein's E equals mc squared. You can also take a deuterium and a tritium atom and squeeze them together to make a standard helium-4 nucleus and an extra neutron and more than 17 mega electron volts. You can also take one of those deuteriums and one of those helium-3s and make a helium-4 and a hydrogen, and then another 18 mega electron volts, and then you've got an extra hydrogen that can then absorb a neutron and become deuterium and get together within the deuterium, and you can start this whole cycle again. And this sort of thing can go on for millions and billions of years until you start to use up the hydrogen. And eventually, a star like Betelgeuse starts to use up that hydrogen, and it spends more time taking heliums and fusing them together to make lithium, and lithiums together to make even larger atoms, and so on and so forth. But there's less and less energy produced doing this, and eventually it's a loss, and eventually that star will collapse or die out, and there's a lot of different mechanisms under which it can happen, and that's a whole nother panel. But basically, this is the way the sun is producing the light that you're seeing. It's producing a lot of energy through these nuclear fusion processes, and eventually that energy can reach the surface of the sun and radiate out into space as light. And while it took 10 to 100 million years for that energy to get from the core to the surface, once it leaves the surface, it takes a little over 8 minutes to reach the Earth at the speed of light in a vacuum. See. All right. Well, how does this relate to northern lights? Well, again, we're talking about the sun. The sun has a very strong magnetic field. The motion of that plasma, of those charged particles inside the sun, generates a strong magnetic field. And it also produces a lot of weird localized magnetic field effects. Sometimes when the magnetic field becomes really twisted and complex up at the surface, these turbulent regions are cooler than the areas around them and they look darker, and we call these sunspots. And these sunspots will sometimes end up blasting a large amount of energy out at once in the form of solar flare, and other times they will just throw off tons and tons and tons of these charged particles in the form of a coronal mass ejection. And the picture you're seeing here is from a coronal mass ejection that happened in 1989. You can see these filaments from the sun erupting forward, and those charged particles then fly out into space. And if a planet like the Earth happens to be in the path, they can hit the planet. And there can be some consequences for that happening. All right. Well, again, those big sunspots and sunspot clusters, as I said, can burp out tons of charged particles into space via those solar flares and coronal mass ejections. And if aimed toward the Earth, these can create intense auroras, because we have our own magnetic field that protects us. I'll get more into that in a moment. There can also be disruptions to radio communication. Those flares are an intense burst of radiation, sometimes in the X-ray spectrum, sometimes in other spectrums. And this can interfere with radio communications. It can interfere with satellite communication with the Earth. It can interfere with the way a plane navigates. It can even interfere with the power grid, as happened in 1989 with one of those coronal mass ejections in Canada, in Quebec. Now, the picture you see at left is a picture that I actually took myself with a Nikon camera through a small telescope using a solar filter on May 11th. And if you look over to the far right of the sun there, you can see a massive complex of multiple sunspots. Those sunspots, a few days before, erupted in a very large coronal mass ejection, which hit the Earth on May 10th. And that geomagnetic storm that happened on May 10th was so intense that the northern lights were not just visible up in the northern latitudes and the southern ones just in the southernmost latitudes. They weren't just visible up near the poles. They reached as far south as Puerto Rico. And it had been almost 100 years since we'd had a coronal mass ejection so strong that northern lights were seen in Puerto Rico. But it can happen. All right. Well, again, how does that work? The Earth actually has a pretty strong magnetic field as far as planets go. And that magnetic field kind of protects us with a kind of a force field out in space. So when those charged particles from the sun get near the Earth's magnetic field tries to redirect them away. Some of them will reach the Earth, but they're redirected towards the north and south magnetic poles. Which one does it go to? Well, it depends on whether it's positively charged or negatively charged, right? So it's going to go to one pole or the other, depending on that. So we do have southern lights that are sometimes visible in Antarctica and sometimes as far north as Australia and New Zealand. And we have northern lights that are often visible up in the Arctic regions in Iceland and Norway, in Alaska, but sometimes they reach as far south as Minnesota, and in an extreme case in May, they can reach the tropics. Now, when these particles collide at such a high speed with the atmosphere and the atoms and molecules in the atmosphere, it can take the electrons that are in those atmospheric elements and jump them into an excited state, if you remember that from chemistry. So you've jumped up energy levels. The electrons would rather be in a more stable, calmer state, so they'll eventually jump back down, and that releases energy, and that energy is in the form of very bright lights. And those are the northern lights you're creating. So literally the northern lights you are seeing are created by the collision of particles from the sun with particles in the Earth's upper atmosphere that are then releasing energy in the form of light. Okay, so aurora can come in many colors. The green are the most common ones you're going to see. And these are caused by collisions with oxygen molecules at altitudes of anywhere between 60 and 190 miles in the atmosphere. So that's above the layer we are living in. That's like stratosphere and beyond. What does the green look like with your eyes? It can look green. It may look more white or gray. Your eyes, unfortunately, are not as well tuned to see the northern lights as, say, a camera is, but sometimes you will see a faint green tinge to things. Another thing that can happen a little less commonly when particles collide with oxygen in those higher altitudes, above 180 miles, is you can produce a red color. And green is more energetic than red, so apparently that collision must not be quite as strong. Sometimes when the particles are able to penetrate down to 60 miles or under, this is rare, and you're only going to get this with the stronger geomagnetic storms like that one in May. You can have collisions with the nitrogen in the Earth's atmosphere, and nitrogen is actually the most plentiful element in Earth's atmosphere at about 73%. And those are going to create more blues and purples. So you will sometimes see a mixture of greens and reds with some blue and purple woven in, depending on how strong the storm is. And occasionally, and I think these are seen mostly in the more northern or most southern latitudes, sometimes during those strongest geomagnetic storms, those greens and blues will mix together to make it look more of a yellow or a pink. Those aren't real common to see. All right, so let's talk about 2024. 2024 has had some amazing northern lights. Again, I've lived in Minnesota for 20 years. There have been northern lights in that time. There haven't been really strong storms most of the time, so they haven't always reached Minnesota. When they haven't, they haven't always been the most brilliant, easiest to see. And in May, it really got my attention because this was a strong storm. So I heard there was a storm going on. I held my iPhone up to my deck window because I was seeing hints of the greens and the reds here. But it wasn't as obvious as when I took a picture with my phone. The phone camera is much more sensitive to these colors, picks them up at a much lower light level, and the phone camera really came through and showed me the northern lights that night. And again, up in the corner, I've got that sunspot complex that caused this. Now, obviously, when I took that picture on the 11th, the sun was turning away from us at that point. The sunspots were moving away. But if you figure that this storm that hit us on the 10th probably left the surface of the sun on the 7th or the 8th, that sunspot complex was dead center when things were shot in our direction. So, yeah. And this was just taken, again, through my sliding glass door on the north side of my house in the northern suburbs of the Twin Cities. I live close to highway lights. There's plenty of city light. I could still see these. On August 11th, again, we had some pretty brilliant northern lights going on because of one extremely large sunspot complex. And again, if you see in this photo, it's mostly green. You're not seeing as much of the red and the purple for this one. To me, looking out the window, this looked like a lot of white. At first, I thought it was just high clouds. But by watching it over a couple of minutes, I could see the way it was changing. And it was changing faster than clouds would. It was very clearly northern lights. I went out the next day and took the photo of the sunspot you're seeing there. And actually, it might have been the day before. That photo of the sun you're seeing there was not taken with a telescope. I literally took a pair of eclipse glasses I had left over from last April's solar eclipse and put them over my iPhone lens, held my phone up, and pointed it at the sun. And that's how I took that photo. that sunspot was so large it showed up even at such a low resolution. So this was a single sunspot that was a much larger complex than the one in the previous photo. Now again in September, we had another event on the 16th of September. And again, you can see some greens with some reds as well. You can see there also are some clouds in that photo. Those are the more solid white things you're seeing above. And you can see some stars scattered about. And again, this was just taken through an upper window, like my bedroom window in my house. I got smarter about taking these photos after the May event and actually went upstairs where I had a better view over the tree line. And then on October 7th, we had another brilliant event, and these northern lights were amazing. They were covering a much higher into the sky than some of the other events. You can see there's an awful lot of green there, but you can see some red or purple over there on the right-hand side. And I even started experimenting around a little bit with time-lapse photography. I will tell you that trying to do time-lapse of northern lights with your iPhone or your Android phone, it's going to be a little difficult because you need to hold the thing steady for several minutes to get a decent video. However, this event didn't get so much publicity. This was like a Sunday night or a Monday morning when I was taking these photos. A few days later, on Thursday, we had plenty of warning about another major geomagnetic storm, another one that reached Florida. And for this one, I actually went out to a lake and was shooting these over the lake. And I was actually amazed that these northern lights, these auroras, were covering so much of the sky because they were reaching so far south. They were covering the whole sky that looking to the north, I actually wasn't as good a view as I was getting looking to the west across the lake. So this is a picture taken west across the lake as these auroras were basically moving by us and heading south. And again, you can see these curtains of green and red in the atmosphere, the few stars peeking through. All right, well, so why were there so many auroras in 2024? Sunspots are going to vary in intensity, and that's over a roughly 11-year solar cycle. Is every one exactly 11 years? No. Some of them are 8.5 years long. Some of them are 13. The average is about 11 years. And some astronomers will actually talk about a solar cycle as being 22 years rather than 11. And I'll get to that more in a minute as to why. But if you consider an 11-year cycle, astronomers have carefully observed 25 continuous solar cycles since 1755. There were sunspots observed far before that. There were Chinese astronomers observing sunspots 2,000 years ago. But we have good records going back 25 solar cycles, back to 1755. And this has given us a better understanding of how sunspots relate to things like the northern lights and also to climate on the Earth. If you remember the Doctor Who episode Thin Ice with the fair out on the frozen over Thames, that was a period of cold caused by volcanism. But there were also some other periods in the Middle Ages where the sun went through some calmer solar cycles like we've had recently. And that did cool the Earth a little bit. And the winters were a little harsher. And actually a better example I think of that was if you think of Valley Forge with George Washington crossing the Delaware and how horrible that winter was. Had more to do with a quieter solar cycle influencing the weather on Earth and making the winters a little more harsh. More sunspots are generally going to occur near the maximum of the cycle, and you're not going to see as many at the minimum. And the maximum is when the sun's magnetic field is becoming increasingly turbulent. And eventually it becomes so turbulent it flips over, swapping north and south. So yeah, this happens about every 11 years where the sun's north pole becomes its south pole and vice versa. No, this is not the rotational pole. It doesn't start rotating in the opposite direction. This is just the magnetic pole, what a compass would pick up. The Earth goes through this as well. Okay, so right now, what we call the Earth's north magnetic pole lines up with the north rotational pole. But if we wait long enough, eventually the magnetic pole is going to flip, and the south magnetic pole will match our north rotational pole, essentially. And what we consider the south pole right now will become the north magnetic pole. And then that'll happen again at some point down the way. How often does this happen on the Earth? It's not every 11 years. It's more like every 100,000 years. How do we know this? In the Atlantic Ocean, there is a rift in the Atlantic Ocean where Europe and North America are moving further apart all the time because there is volcanism in the center of the Atlantic Ocean, bringing up new magma, creating new ocean floor, and spreading the ocean out, spreading the ocean floor out. If we look at the iron particles that have been trapped in the rocks there, as that magma comes up and cools, they orient themselves to the Earth's magnetic field. During periods where the North Magnetic Pole is up in Canada, the iron particles are going to orient themselves in one direction. And when that North Pole is down in Antarctica, they orient themselves in the opposite direction. And if we look at the geologic age of these rocks about every 100,000 years, it flips. Okay, so again, in the sun, this happens about every 11 years where the sun's magnetic poles flip over. And that process of getting that point really stirs the sun up. You're going to get a lot more turbulence in the magnetic field and a lot more sunspots. And we've seen that in 2024. There's been a lot more sunspots in 2024. But what's really interesting is the last two solar cycles have really been quiet. So the last 20 years, we really haven't seen that many sunspots. Have we seen them? Yes. Have there been solar flares? Have there been coronal mass ejections? Absolutely. But not in the quantity that we saw in previous decades, and not as many super strong ones either. And now we are seeing a lot more sunspots, a lot more activity, a lot bigger sunspots, a lot bigger coronal mass ejections that have created these crazy events. Now, if we think back to the 80s, again in 1989, there was some really strong stuff going on in 89, and one of those strong coronal mass ejections actually knocked out the power over Quebec. There was a very famous, very strong geomagnetic storm back in the 1800s known as the Carrington event that, if it hit our current society, would have knocked out power probably over a good part of the world. It was disrupting telegraph wires and causing all kinds of problems because you had so many charged particles coming from the sun, penetrating the Earth's atmosphere and moving around. And when we have a charge moving around, it creates electric fields, it creates magnetic fields. If you do this to existing wires, you can generate electricity in wires where electricity wasn't there. You can take a telegraph wire that wasn't transmitting anything, and suddenly there's electricity running through it, and the telegraphs went crazy. And in some cases, you can burn them out because there's too much energy pouring through them. And that's basically what the power grid did in Quebec in 1989. So we do have to be concerned about a major coronal mass ejection or solar flare event happening because we can be affected. All right, well, so things are heating up. So we are at this point believing that the solar maximum is approaching. We think 2024 is a ramp up. It's probably going to hit that maximum sometime in 2025, maybe sometime in 2026. But finally, the sun is very much woken up in a way that it hasn't in a few decades. And so we are likely to see more northern lights scattered across 2025 because of this. Are they going to happen every day? No. Are there particles from the sun raining down on the Earth every day? Yes. Usually the quantities are quite small. If you see any auroras, northern light type effects, it's going to be only close to the poles. But when those larger events happen, it pushes further south. We see it further down. We see more light. We see more activity. All right, so how do you know when to look for it? There are three good websites I want to point you to. First of all, NOAA has a Space Weather Prediction Center. This is a government agency, part of the National Weather Service type organization, and National Weather Service is part of NOAA, National Oceanographic and Atmospheric Administration. They track sunspots, they track auroras, they have telescopes looking at the sun every day, and in fact, the telescope that they usually use for these observations is at Stanford, and it is currently down because it was damaged during some bad weather a few months ago. but there are other telescopes out there that are filling in the gap right now. A fan site that does a great job of taking that NOAA data and other observer reports from around the world and discussing sunspots and aurora activity in friendly language that anybody can understand is spaceweather.com. And this is the one I really was using this year to know when each storm was coming. Yeah, we all heard about the May 10th and May 11th event on the news, but how did I know about August and September? Because I was watching spaceweather.com. I'm recording this today on January 4th, 2025. There was a coronal mass ejection in the last couple of days that struck in the wee hours last night, and spaceweather.com alerted me to this. I was trying late last night to see if I get some photographs of northern lights, and I was getting mixed results. I know in some parts of the world they were definitely seeing it. I was getting some mixed results here in Minnesota. I'm not sure I was really seeing what I thought I was seeing, but this is how I know when to look. They've also been tracking some other astronomical things, but they are primarily focused on the sun. There's also a lovely little site called Aurorasaurus. So Aurora, again, are your northern or southern lights, and Saurus like a dinosaur. It's got a cute little name, but it gives you an opportunity to report on you seeing northern lights where you are. And you can even share your own pictures and observations on the site. And then with this aggregate data, you can kind of give a better idea of just how far extent it reached across the world that day. So yeah, these are a great way to go. So what's the best way to actually see and even photograph the auroras? First of all, it helps to get away from the city if you can. I have not for any of these events. I know several of my friends back during the May event drove north, got out of the Twin Cities to some dark areas. I have a friend in Michigan that drove 3 hours north into the upper part of the lower peninsula, got some brilliant photos. But you get away from the city lights if you can. But for some of these stronger events, you can see it in the cities, especially if you use your camera. Clear skies, as always in astronomy, are helpful. I can't tell you the number of major astronomy events in my life have been ruined by bad weather. In 2017, I had all kinds of plans at my library for an event to help hundreds of people watch the eclipse safely, and we got to see it for about 20 seconds before the clouds rolled in and it rained. So, weather can be a problem. If you are going to observe from home, I recommend turning off your porch light and any room lights because these are going to ruin your night vision and they're going to cause distractions for your camera. If you're in your car out somewhere further north, turn the headlights off. Obviously when you're parked, but turn those headlights off, try to get away from the street lights and things, and give your time to adapt to the dark. Okay, the longer you wait for your eyes to adapt to the dark, the more you're going to be able to see. Typical human being needs about 20 minutes to fully adapt to the dark. And if you spend a lot of time looking at your phone in there, the bright light on your phone is going to ruin that. So just try to give it time, sit in the dark, let your eyes adapt. You will see more stars, you will see more color. And when it comes to the auroras, same thing. You're going to see more detail, you're going to see more color. I happen to be a little more advanced than most people. I don't know if it's because I spent so much of my childhood out with a telescope, or if it's just because my eyes are just more tuned this way. I am very light sensitive in bright light. I'm basically blind on a bright day because it is too bright for me, but I see well in the dark, and it takes me about 10 minutes to fully adapt, where it takes the average person 20. I also see more color in the dark than the average person. I have no trouble distinguishing Betelgeuse's red from Rigel's blue when I look at stars in the night sky. I can also see a limited amount of color in a dark bedroom, which most people do not see. And then key thing, of course, is if you're in the northern hemisphere, look north. If you're in the southern hemisphere, reverse this, okay? So if you're one of our friends from Australia visiting the con, look south. You're also going to want to get above the tree line as best you can because trees are going to block your view. Auroras may stick closer to the horizon depending on how far they're spreading. Obviously, in that October event, they were all overhead. I was seeing them to the north, I was seeing them to the south. But many times you're only going to see a thin line of them to the north, and the trees might be blocking your view. That may be why I wasn't seeing them last night. And then, again, you may not see all the detail, you may not see all the color. But if you take a photo with your phone, and again, turn your flash off, Make sure it's taking one of those 3-second exposures. You're going to have to hold your phone steady. It's going to pick up more color and more detail than your eyes can. Can you do this with a fancier camera? Absolutely. If you pull out your Nikon and your Canon or your Sony and fiddle with your f-stop settings and all, you can take some brilliant pictures of these things. You can also do some brilliant time-lapse with a DSLR. Again, I said you could do it with an iPhone or an Android phone, but you're going to have to hold it steady for a while. For the October event where I went out to a lake, I actually brought my Nikon with me and set it up on a tripod. I was using the iPhone to take stills. I was using the Nikon to try to do time-lapse photography, and what I was doing was slightly longish exposures every so many seconds over the course of several minutes. And I did get some nice motion of the Northern Lights videos with that unfortunately are kind of hard to share on here. But that was my first attempt to do that. I'm hoping if there are some more events this year, I'll be able to do a better job of capturing some good time-lapse videos of the Northern Lights here in Minnesota. All right. Well, I've moved along through this talk fairly quickly, but I think I've given you a good basic overview of what the solar maximum is, how the activity in the sun relates to us seeing the Northern Lights, and there you go. I think I've given you some tools to work with. If you're still curious about some things, I do encourage you again to go back and check out spaceweather.com in particular. A lot of good information up there. Also, I'm happy to answer some questions on the Console Room Discord, or if you leave some comments on the YouTube. Once this goes on YouTube, I may be able to answer some questions there. And again, this isn't my particular expertise in astronomy, but I'm certainly happy to sort out what I can. Also, I just would like to mention that we have done a number of science panels at Console Room over the years. Some of them were only live back before the pandemic, but as we've become a hybrid con in recent years, some of them are recorded and still on YouTube. So here's a sample of some of our past discussions. 2 years ago, I did a talk about the history of space telescopes. We've also had others talk about real-life crinoids, healthcare professional appreciation. That was my wife and a social worker talking about what they dealt with during the height of the pandemic and how they had to adapt to that. My wife's also been involved in a panel about pandemics in Doctor Who, and I believe she and Stacy are doing one about pandemics this year as well. And I also was involved in one about climate change in Doctor Who. And some of the topics I discussed today even entered, with solar activity, even entered into that panel. I've also done some science talks at Convergence in the past. You may have seen me talking about the New Horizons spacecraft either at Console Room or Convergence. I was on a panel at Convergence about climate change in Westeros in Game of Thrones. So we're not just about science fiction at this con, we're also a little bit about the science too. All right, well, thanks everyone for coming. Console Room 2012.